Hello students, in today's class we'll see about optimization, finding the best solution. So imagine you have 10,000 rupees given to buy a laptop and you have a different choice of laptops. For example, gaming laptop, office laptop, thin laptop or used laptop or a Chromebook. So which one will be your absolute best choice? So your answer depends on what is that you need. If suppose you need a laptop for a game, you will obviously go for a gaming laptop. So similarly, optimization always depend on the objective. There is an objective for which we go for an optimization. So what is optimization? Optimization is the process of choosing the best solution from many possible solution while satisfying the condition. So the condition is very important to be satisfied in any optimization problem. So what are the common real world optimization? We just achieve, we need to achieve minimum travel time, maximize the profit, minimizing the cost, maximizing the accuracy, minimizing the energy consumption. See, these are the some examples of real world optimization. And to go through such an optimization, what are the three fundamental components? So the three fundamental components are the decision variable. So the decision variable is where the element that you're trying to control or adjust. The second one is the objective function. And the third one is the constraint. So objective function is, it defines exactly what you're trying to achieve or measure. And constraint is the boundaries or limitations when you work on those optimization. So decision variable. Suppose you are designing a drone, right? So there are some parameters which are variables, right? For example, the battery capacity, the motor type, the total weight, the target speed, or the maximum flight height. These adjustable elements are called as the decision variables, right? By definition, decision variables are the specific variables whose value can be actively changed to obtain a better solution. So the second component is the objective function. Here is where the function is or the goal. I can say it is the goal for which I'm going for an optimization. So the goal can be in terms of maximizing my profit, maximizing my accuracy, and maximizing my network throughput. Or the goal can be in terms of minimizing the cost, minimizing the delay, and minimizing the distance and energy. So there are two categories of optimization function. And the third one is the constraint. So obviously, whenever you go for optimization, there can be some limits. So this is the limit with which you can optimize. For example, I can have only the maximum weight of 2 kg, or the battery capacity is limited to exactly 5000 milliamps, or I have the budget, strictly the budget is 30,000. So these are some of the limitations or the constraint on those optimization, right? So they define the strict limit within which our optimal solution must be found. So suppose you imagine an optimal a case study. If you take a case study of a pizza shop problem, so consider a daily operation of a pizza shop. So the owner must solve the optimization problem to run the business effectively. So that can be the decision variable, the number of pizza to bake and the specific ingredients to buy. And what will be the primary objective? Obviously, it will be to maximize the profit by balancing the production cost with the consumer demand. And what could be the constraint? The dough that is available for a day and quantity of cheese in the stock and limited staff working hours. So these three concepts or the components are very, very essential when you design an optimization problem. So what could be the optimization objective? As we discussed, the optimization objectives can be in terms of maximizing the benefit or minimizing the penalties. So benefits examples can be the overall profit, system accuracy, battery life, network throughput, customer satisfaction, and penalties in terms of financial cost, system error, energy consumption, network delay, and customer waiting time. So these three fundamental components, okay, so they are operated on something called the search space. So optimization is nothing but you have to search for the best solution. So the search space represents the complete set of all possible solutions. So you imagine a massive grid composed of countless individual squares. So every square is very unique. Every square can be a possible solution for an optimization. But the best square has to be selected. That is what is the success of optimization. For example, you imagine the circle. This is a search space. There can be something called a feasible region. Feasible region in the sense which satisfies the constraint. Okay, so constraint is very important. So satisfies the constraint. Among the feasible solution, you will have the optimal solution, right? So the best solution. So there can be something called a continuous optimization where which occurs when the problem's decision variable can take the real value, example, temperature reading, exact the physical height, electronic, these are all continuous values. When such a continuous values makes your decision variable, then you call it as a continuous optimization. And the second one is a discrete optimization where your decision variables are very discrete. Example, the number of servers in a data center, the number of enrolled student, the total count of physical network devices, specific routing paths, number of cities. So these are some of the examples of discrete optimization. There is also something called the static optimization. Static optimization is the condition where the environment or the underlying conditions, it remains constant throughout your optimization time. Okay, so that is what is called as the static optimization. And dynamic optimization, the conditions changes, maybe a morning. Okay, so a Google map gives you route A and afternoon it gives route B. Why? Because in the afternoon, the traffic condition is very, very high. In the morning, the traffic condition is less. So here, the optimization has to work on two type of conditions. One is with traffic and without traffic. In this case, it is called a dynamic optimization. It is dynamic optimization is where the environment, the constraint, and the resulting optimal solutions varies continuously and dynamically. So there are also some classical optimization methods. And why should we go for nature-inspired optimization is a question. So obviously this full subject deals about nature-inspired optimization. And why can't we go for classical optimization methods like gradient descent, Newton method, Lagrange multiplier, and simplex search that you learned in your previous semester. So when you talk about the gradient descent, what is gradient descent? You imagine like your hill climb game that you usually play. So there are mountains, there are terrains, there are flat surfaces. Obviously, you have to load your vehicle through those surfaces. So this is called the gradient search method. So that terrains is like your search space. And you have to find out the best solution in that search space, right? The strict limitations is it absolutely requires smooth, continuous mathematical function to work, and it is notoriously easy for algorithm to get stuck in the local trap. For example, you imagine this diagram. So there is a shallow local minimum where your data may get stuck. Your algorithm may say that this is the best solution, 3, 4, saying that, yeah, this is the minimum value. But obviously, if suppose the optimization problem is taken a little bit more, you can arrive at the best global minimum. Okay, so very, very steep global minimum. But now the traditional mathematical algorithms may settle down in the shallow local minimum. That is one of the problem with the gradient problems like gradient descent, right? So the classical optimization failures, they struggle significantly when the optimization function is unknown or acts as a black box. They also fail when the mathematical function is discontinuous. They fail when the search space is very large. They fail when the landscape contains many deceptive local optima. And it is really highly a complex NP hard problem. But what about and complex computational domains? There is also the search domain is very complex. You imagine the case of a traveling salesman problem. If the cities is 10, fine. If the cities is 100, okay. If the cities is 1,000, complex. If the cities is 10,000, it is very large. You think of number of servers in a data center. Okay, the number of switches connecting those servers, the number of network paths. So obviously, whenever you want to have an optimized traffic in such situation, this classical search methods will create a bottleneck. Okay, they cannot plan accordingly. So that is where we go for the nature-inspired optimization, where birds or ants or bees, they do not have any mathematical calculation. Okay, so they use their absolute intelligence, they use their absolute collective intelligence sometimes to go for this optimization. So how do we do this optimization journey? You take a real problem, you frame it to be an optimization problem by having the decision variable, by forming the objective function, and you just frame it, and then you form the constraints. Okay, so on what constraint is going to work. Okay, so you create a search space, then apply those nature inspired techniques, okay, to overcome the limitations of the traditional mathematics. So this is your optimization journey. Whenever you find a problem, first you write an objective function. That is the foremost first step. Second, you define the constraint. Third, you tell where all you have to search using this constraint and objective function, where all the program has to search. Then it will navigate towards the best solution. So this is about the optimization. In this lecture, we saw about the three components of optimization, different types of optimization, and what is the difference between the classical optimization method and the nature-inspired optimization method.